Greetings, calculus student watching this video. This is a recap of what we discussed as we entered into chapter 7 of our text. We're kind of doing some prior knowledge work here first, focusing on area. So area, bounded area, I'm picturing it here, I'm showing you a visual. So for this function, I'm showing it at this interval. These happen to be the x-intercepts, -2 and +2. I'm liking to find the area. Here's the wrong way to do it. The common wrong answer would be to accumulate from -2 to 2 on this function, because what you will end up getting is a big fat 0. And there's area there. I know there's area. I see it. There's area here. There's area there. The reason your calculator is telling you 0 is because your accumulations are canceling each other out. Area and accumulation are not exactly one and the same, because accumulations can be negative and area cannot. So the negative accumulation here completely undid the positive accumulation there. But nonetheless, we are not talking about accumulation, we're talking about area. So, a wise person once said, if you want something to be positive and it's negative, you can use the absolute value. So, what I would suggest here is a breakdown. So, accumulate from -2 to 0 on the function. See what the area is. It won't always be a nice symmetric curve like this. You'll find that that's -4. However, that's not an area. So, if we take the absolute value of that, kind of manually just call it an area of 4 square units. That is an area, yeah? We continue accumulating all the way through the intervals. So, again, from 0 to +2 this time. This accumulation will be positive, as we can see in the picture. It will also come out to a positive value as is. No need for absolute value here. We have 4 units squared with 4 units squared. So the total area, wow, hard to write with my finger here. Total area bounded by this cubic function is 8 units squared. Final answer, not 0, 8 units squared. Now if we explore this cosine function quickly, so long as I've drawn the picture correctly, that's a height of 2, our equilibrium is 1, this is where some function knowledge comes in. If I go from 0 to pi, I can't say that I've drawn that perfectly here, nor have I shaded the accurate amount of area, but noticing that everything here is above the x-axis, that would indicate that those areas and accumulations are both positive. So there's no need to do any excessive handiwork here. You can just accumulate here from 0 to pi on 1 plus cosine of x, because everything's already positive. No stress, the area will be the accumulation, one and the same. So antiderivative, and you're on your way. So evaluating 0 to pi, the upper boundary evaluates to pi plus sine of pi, which is 0. And then 0 and sine of 0. Lots of zeros there. The final area here will be pi units squared. Notice I'm labeling with units squared. Some people were doing that a little bit too much in the accumulations just when we learned about integrals, but here, because we're being asked for area, our label must be units squared. Why all this talk about area? Well, have you ever noticed or thought about the concept of area is similar to the concept of distance? I remember us talking about this with my, what class was that? Geometry. In geometry, we always found distance, and there was a formula, and there was Pythagorean theorem, and all that good stuff. But distance, you would know if you were solving a problem it didn't seem right if you got a negative distance, because that's not realistic. So, negative distance is not realistic. I'm reminded of a movie from the 80s, Ferris Bueller's Day Off. This is my favorite example of distance not being negative. The kid borrowed his dad's car without his permission, drove it. His dad was a fanatic about his car, recorded the mileage even, like every time he drove it. So the kid knew he was going to get in trouble. He tried to put the car up on like jacks and put it in reverse to undo the mileage. That did not work, because that just added more mileage. Even when the wheels were spinning backwards, distance was being accumulated. You were driving the car backwards is what the car thought. More miles added to the tachometer, I think that's what it's called. So, okay, the concept of area is similar to the concept of distance. Just like negative area isn't a thing, it's not realistic because we can't have like negative dimensions. We have negative directions, and that's where physics comes in, but we cannot have negative dimensions. So realistic it is not. And so I'm going to draw a big plus sign here. Both of these things must be positive. Now, if you can calculate an area, you can probably calculate a distance. They are both accumulations, if you want to make a note of that. One is an accumulation just for like a curve and the dimensions of the curve, or the heights and widths and such. Accumulation, though, to find distance will be based upon an accumulation. Well, let's just do a simple one. If I want this accumulation to be distance, this axis is probably time. How long does it take to travel a certain distance? Well, that would depend on the speed. Maybe we call it velocity. More often we call it velocity, but these like miles per hour multiplied by these hours, that area does end up being just miles. So we are accumulating under a velocity function of sorts, or the speed function, if you will. If you've never heard the word displacement, it is not exactly the same as distance. So maybe take a moment to pause the video and think. Jot down a few ideas about the difference between distance and displacement, and then they will be defined. So here we have it. Displacement is defined, like I said it would be, by a change in position from starting point to ending point. So in this lovely picture, I've got the classic example of a bug. This x of t represents maybe its position on some sort of vertical axis, and so that means the bug is climbing up, it's climbing down, but it starts right here. See it? Looks like a bug. Where is it at the beginning? Here. Where is it at the end? Here. So it started out in displace, and it ended in displace. That's me being silly, but it's just a change in placement. Now, it looks to me in this example as if the displacement for this example is 0. The bug is neither above or below its starting point, so its net change, if you will, is 0. That's a 0 displacement. Now, is this 0 distance? Absolutely not. 0 distance would mean the bug went nowhere. It obviously went somewhere, and now every time it changes direction, you would want to kind of think about it. Well, it climbed up. How far did it climb? You could maybe even count that if you had labels on this axis. It went from here to here. And then it climbed way down, 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 down. This is distance traveled. Do not get confused with negatives and positives here with rates of change. Even though it's climbing down, it's still moving. It's not like this amount of movement will undo this amount of movement. No, this is all positive. This is all positive because we're talking about distance, remember. Every time it changes direction here, you could look at how far it has moved. Okay, how do you calculate that? That will be our final example. Example. Find where the particle, so it's no longer a bug, we have an example of a particle here, where the particle changes direction. Do that. Don't skip that part, because that is important. That is like putting the ball on the tee for you. If you can find where the particle changes direction, notice we've been given a velocity function this time, not a position function, then that'll help you to determine especially the distance travel. So I like to visualize and attack problems. So my sine function, that pi times t, is changing the period of the graph. So we'll still kind of go above and below, with a period of 2. So that will be 2. This is probably 1. I know it's 1. This is 4. Oopsie daisy. I can probably move things like this as a smartboard. Yeah, it moves just like my smartboard. And then this would be the last little part of the jaunt to 5. Remember, these are velocities and these are times. So it's changing direction. How often? Well, change in direction is whenever the velocity is 0 and there's a change in sign. So the change in sign, SIGN, occurs here because we have positive velocities changing to negative velocities. These are all negative down here. It also changes here at 2 seconds, positive, from the negative to the positive. Oh, it's changing a lot. Changes here at 3 seconds and at 4 seconds. It changes every second. So that's important to note. Well, why? If we know it changes every second, that helps us with displacement, because displacement is a relative measurement from the starting point. Granted, we don't know where that is, like position-wise. From that starting point, this particle is moving, let's say, to the right. This is positive velocity, remember. When it moves to the left, negative velocity. In this moment, it's back to where it started. At 1 second, it was far to the right of where it started. It kind of went back to where it started, and it also came back to where it started here at 4 seconds. So in the very end, this little amount of movement is going to be the ultimate displacement. So I'm just going to look at one of these little bumps from 0 to 1 on this function. Whatever this number ends up being, that will be our amount of displacement, and it should be positive because this is the only part that did not get undone. So positive and negative, this is like the net accumulation where you consider positives and negatives. Imagine a person walking forward and then backward. They're back to where they started. That's their displacement. That would be displacement 0. Here we do not have displacement 0. Pause the video if you'd like to find the antiderivative. That's what I'm going to do and evaluate it quickly. So here's my work. That's a negative 1 over pi times the cosine of pi t. If I evaluate, the cosine of pi is negative 1. So that would give me positive 1 over pi, and the cosine of 0 is positive 1. So these have a common denominator. Our displacement is 2 over pi units, whatever those are. We don't know if they're feet or meters or what. This is not the same as the distance. Distance, because we know about all the symmetry of this lovely function called sine, those distances would all be reproduced. You're walking this far forward, this far backward, this far forward, this far backward. If you were wearing one of those step meters, all of those movements would be counted in your steps. So we need to accumulate 1 of the 2 over pi's. 2 of the 2 over pi's. This is how much change is occurring. And notice I'm not writing any negatives. These are all total distances. 2, 4, 6, 8, 10. 10 piths. And that is our total distance. Accumulating only positive values. The velocity multiplied by time would give me that distance. In other words, this area represents the distance. Be careful as you work through displacement and distance problems. Be mindful of change in direction. If you are going to use your calculator, one last little tip. You can accumulate under a velocity function in order to find distance traveled, but you have to make sure you have only positive velocities or speeds. The best way to do that is to use the absolute value sign, and that would essentially make all these little bumps above the axis, right? Do not do the absolute value after, because you might be already undoing all the distance that you've traveled. Absolute value of velocity function, and then accumulate from whatever time to whatever time. That's the end of this story. Mrs. D signing out.